All right, welcome to The Explainer. Today, we're diving into a major crack in our understanding of the universe. It's a problem that's so stubborn it's actually forcing scientists to question, well, everything they thought they knew about reality itself.
So, what's all the fuss about? Well, it boils down to a question that sounds super simple. How fast is our universe expanding? Seems straightforward, right? But for decades, scientists have been trying to pin down that number, and they've hit a massive roadblock.
And here is the roadblock. Depending on how we look at the universe, we get two totally different answers. So when we look way back in time at the afterglow of the Big Bang, the universe as a baby, we get one number. But then when we measure things closer to home using nearby galaxies, we get a completely different number. And these two answers, they just don't line up. Not even close.
Now look, we're not talking about a tiny rounding error or some small calibration issue here. This is a big, glaring, persistent conflict between our two best ways of measuring the cosmos. And it's such a big deal, it's got an official name, the Hubble tension.
So to get to the bottom of this, scientists did what scientists do. They built some absolutely incredible machines. For 15 years, this amazing piece of tech, the Atacama Cosmology Telescope, sat high up in the Chilean desert and just stared at that ancient light from the Big Bang, trying to make the most detailed map of the early universe ever. So after all that time, after a decade and a half of painstakingly collecting data, the final results are in. And you'd think this would be the moment that solves the mystery, right? Nope. Instead, it confirms something, well, kind of awkward. The problem isn't some mistake. The conflict is real, and it is not going away. So where does that leave us? We're at this major fork in the road. You basically got two ways to look at this. Option one is, hey, everybody calm down, the data's just messy, we must have missed some errors somewhere. But option two, that's the big one. It's the possibility that something in our fundamental story of reality is just wrong. Of course, the science team didn't just throw their hands up. They tried to save our current standard model of cosmology. They came up with about 30 different small patch ideas to try and fix the leak. Adding new kinds of particles, messing with dark energy, that sort of thing. But here's the thing about having such good, clean data. It's really good at telling you what's not working. And it basically shot down all those simple fixes, one by one. The message from the team was pretty blunt, actually. Your favorite little pet theory? It probably doesn't work. Okay, so if the little patches don't work, where do we go from there? It forces us to ask a much bigger and, frankly, much more uncomfortable question. What if we don't just need a patch? What if we've been telling the wrong story entirely?
And this is where things get really interesting. See, when the old story starts to crack, it makes room for brand new ideas. And one of these new perspectives, a different way of looking at everything, is called motion theory. It sees a problem like the Hubble tension not as a failure, but as a really important clue.
So motion theory starts by rethinking the absolute basics, starting with time. It says, hold on, what if time isn't some universal river that we're all floating in? Instead, what if time is just what we get when we count stable, repeating motions? It's a way of measuring, not a container.
And it does the exact same thing for space. Space isn't an empty box that stuff moves around in. No, space is the property that tells motion where it can go and how difficult it is to get there. It's a description of motion's possibilities.
But here is the real kicker, the part that connects back to our mystery. It completely redefines dark energy. In this view, dark energy isn't some strange, mysterious substance pushing the universe apart. It's simply the large-scale effect of motion in the universe becoming less orderly, less coherent over billions and billions of years.
I know, that's a lot to wrap your head around. So let's use a simple analogy to make this crystal clear.
Okay, I want you to picture the early universe as a giant cosmic drumhead. Everything is beating in perfect time, a completely synchronized, ordered pattern of motion. But over billions of years, that perfect ordered beat starts to leak out. It transforms into things like heat and the expansion of space itself. Now that cosmic microwave background we keep talking about, it's like a snapshot of that original perfect drum pattern. And the Hubble constant, that's just us, today, measuring how much that pattern has stretched out since the beat began. Now, here's the crucial part. Our current standard model of cosmology has a very specific assumption baked into it. It assumes that this leakage of ordered motion, what the theory calls coherence decay, happens in one very particular, predictable way.
But motion theory comes along and asks a really powerful, simple question. What if that core assumption is just a little bit off? What if the way this cosmic rhythm decays over time is even slightly different from what our models predict? And this is the potential aha moment. Because if you allow for a slightly different decay rate, you could get a universe that does two amazing things at once. It could perfectly match that detailed map of the ancient drum pattern seen by the ACT telescope while also giving you a faster expansion rate today, a rate that just so happens to match exactly what we see in our local galaxies. It could solve the entire tension in one go.
So from this new perspective, that ultra-precise result from the ACT telescope isn't a problem at all. It's not a dead end. It's a giant, flashing arrow pointing us toward a totally new way of thinking. It's a very loud clue.
And this brings us right back to our original question. After everything, is the Hubble tension just a bug? You know, a simple mistake in our measurements or our math that we just haven't spotted yet?
Or, and this is the really exciting possibility, is it a feature? Could it be a genuine signature of how the universe actually works? A fundamental clue telling us that the cosmos operates in a way we never expected. Which leaves us with this truly profound thought to chew on. Maybe the fix isn't another little tweak to our equations. It might just be that we've been telling the wrong story about what time, what space, and what dark energy fundamentally are all along.
So in our next explainer, we're going to dive even deeper into this. We'll explore exactly how a universe built from the ground up on these motion-first principles could naturally give rise to the Hubble tension, not as a cosmic bug, but as a core feature of reality itself.